Welcome to Module 6. In this module, we'll look at ocean circulation patterns. For example, the western boundary current that we see that's depicted in the satellite image to the right. In this module, we'll be focusing on currents, what are surface currents, how we study and track surface currents, the different types of surface currents. We'll talk about how surface currents are organized in things called gyres. We'll look at a concept of Ekman spiral and Ekman transport, which will explain movement of water within the ocean. And this is movement irrespective of waves. We will talk about upwelling and downwelling currents, a little bit about thermal haline circulation, the vertical movement of water within the oceans. And we'll end off by talking about El Nino and La Nina, two weather-based phenomena that are intimately intertwined with the ocean and what happens in the ocean. What is an ocean current? An ocean current is a continuous directed movement of water from one place to another. So we have a water molecule. That water molecule is moved by point A to point B by usually one of two forces, by the force of wind blowing across the surface waters or by gravity as we move into deeper and deeper waters. So this movement is the result of a number of different forces. In this image that's been colored and modified by NASA, we can see current patterns within the Atlantic Ocean. You can kind of see Nova Scotia up towards the top of the image in Newfoundland. And here we see colored with sea surface temperature data, but the presence of a number of different currents within the ocean. Within the ocean, we see two sort of main types of currents. We have surface currents. So these are currents that are driven by wind, and it's the horizontal movement of water along across the ocean surface. And then we have currents that are driven by density. So gravity will pull colder, saltier, denser water downwards. We call these thermal haline currents. Thermal for heat, haline for salt. These are deep water currents, and we see that these are responsible for sort of the vertical movement of water within the ocean. So bringing water from the surface of the ocean down into the deeper parts of the ocean. We find that these thermal haline currents operate sort of as a global scaled conveyor belt, with cold water forming in two locations on the planet, and then this colder water traveling through the deeper parts of the water, eventually making its way to the surface where it warms, and then at some point sinks again and becomes this cold, cool subsurface flow. Humans have known about the presence of ocean currents for a long time. Greeks, we know, back in 900 or 700 before Common Era, once they ventured out into the Mediterranean and the Atlantic, they observed the presence of a current, sort of this river of water flowing in the ocean, moving from north to south. And this is once again just a reminder why we call oceans oceans. The Greeks gave this a term okeanos, which in turn became our modern day word ocean. The current that they discovered, as we'll find out later on this lecture, is a current called the Canary Current, which moves along the westernmost coast of Europe, England, Spain, Portugal, and Western Africa. In the 17th century, Japanese fishing fleets took advantage of a current that we find off the coast of Japan. This is a current that we know that is called the Kuroshio current. And what they would do is basically drift in the current up to the really fish-rich waters off of the Kamchatka Peninsula that forms part of the easternmost portion of modern-day Russia. Currents were also studied as part of the Challenger expedition. Here you have a picture of Sir John Murray, one of the leaders of this expedition, and they took a look at currents. They realized that the temperature of surface water was usually higher than deeper water. They made note of rapid temperature changes within the water column, and from that they also noted there was a movement, a vertical movement of water. So they do reports of thermal haline circulation, so this vertical current that exists within the ocean. They also recorded on and reported data on currents as they encountered them throughout their whole entire 4-year voyage. In the present day, we have many different ways to study ocean currents. We have direct observation and measurement. We actually get into the ocean, place a probe in the ocean, place some sort of physical object within the ocean, and from there we can observe currents. We can measure the speed at which currents are traveling. We can also measure currents and study currents from remotely. And this is through the use of satellites and other sort of remotely operating vehicles that such as drones, airplanes, helicopters, anything that lets us view the ocean remotely and study what's going on in the ocean. We also sometimes make use of other material that might be in the ocean. For example, material that is lost during a shipwreck, something that's comprised of flotsam of the ocean. And that's why we have this little yellow duck on the beach right here. One of the simplest and most cost-effective ways to study ocean currents is through the use of drift bottles and drift cards. So basically what you do is it's like throwing a message in a bottle overboard and seeing who responds to your message. Scientists, researchers will go out in a current somewhere, they'll pick a location, they'll mark where this location is, they know where they threw these cards or bottles overboard, and basically they wait for them to drift ashore. They know where the current ends, but they're not too sure what path was followed as these cards or bottles or any other sort of thing that floats is thrown overboard. So what might happen is you might be on a beach, you might pick up a card, you might pick up a bottle. These cards are made out of durable plastic, and you'll see something like this: scientific study, please report the discovery. And they quite often give you an email address or a phone number to phone in and say, this is where I found it on this date at this location at this time. Sometimes if the data is really valuable for them, if they really want to get this data, they're often sometimes a reward attached to this, but not always the case. We can also use more high-tech methods to study oceans. In this case, here we track currents with buoys. Here we see some scientists ready to deploy a buoy into the waters. Basically what it is it's designed there to float in the water. It drifts with the current, usually has some sort of transmitter associated with it, which it then sits there and transmits information about its location, maybe information about the water temperature, the salinity of the water, to a satellite somewhere, and then this information is relayed back to an office at some place on Earth. Other examples of instrumentation used to study currents is drifters. Drifters are things that can be constructed by a number of different methods. You can find plans online. This is something that primary school classes quite often do. Basically, the drifter gets placed overboard. There's a transmitter, once again, which relays data to a satellite and provides data about its location day after day after day. And from this, people can track and study shallow water currents. You want to look at a little deeper water, and currents are moving deeper water. You can also use something that's known as a deep ocean drifter. These will descend to a certain depth. They'll drift with these deeper water currents for a period, let's say in this example, 10 days. And then after 10 days, they pop back up to the surface, recording other data, salinity and temperature changes as it moves up to the surface. You have that drifter there. You might as well make it do as much work as possible. Transmits this information to satellite, which is then once again sent to an office somewhere, and then that drifter returns back to some predetermined depth. Argo represents an international collaboration in collecting data from the ocean about currents and how currents move, the temperature and salinity of the currents. So currently it depends on any given day, but there's roughly about 3,800 free drifting profile floats that are in the ocean, floating at somewhere in the upper 2,000 meters of the water column. Not only do they sort of send information about the direction that currents are moving, but they also send information about temperature and salinity. Once again, these are some of the ones that pop back up to the surface to relay information to the satellite. The Argo program is really interesting in the fact that you can go on, you can Google Argo, you can go onto the site, you can see the location of where all the Argo floats are on any particular day, and you can also download the data that it collects. So as an example, for ordinary citizens to go and collect scientific data or take scientific data, play around with it and see if they can notice any trends or patterns in the data that might be telling us something about the ocean. And then we come to this researcher here, Curtis Ebbesmeyer. And Curtis Ebbesmeyer is an oceanographer, and he studies currents. But what he does is he tracks the movement of material that might be lost at sea. Let's say, for example, consumer goods are lost during a storm. A container gets thrown overboard on a container ship, breaks open. He tracks the movement of this material, this lost material, this stuff called flotsam, floating wreckage of a ship or its cargo, and he uses this sort of as a serendipitous thing by which he can track currents. It definitely is a low-cost way to track currents. That materials in the ocean, you don't have to go out and use ship time or buy instrumentation to track currents. One of the things he's well known for is to track the movement of something known as the friendly floaties. The friendly floaties were a series of children's bath toys that were being shipped from Hong Kong over to the port of Tacoma in Washington, United States. And on January 10th, 1992, about 28,800 of these toys that consisted of red beavers, green frogs, blue turtles, and yellow ducks were washed overboard from a container ship in a storm. He knew where this material had been lost, where this container had been washed overboard, the location, and then what happened is these started to show up on shore. By tracking the position where they showed up on shore, Ebbesmeyer was able to determine where currents traveled. He sort of picked up a circular current pattern in the northern part of the Pacific, a circular current pattern in the southern part of the Pacific, and even tracked the movement of these friendly floaties, these bath toys, as far away as the coastline of England in 2007 and 2003. The friendly floaties are not the only time that oceanographers have been able to track cargo that has been lost at sea. In 1990, there was a storm once again in the Pacific Ocean. Nike shoes were being shipped from Asia over to the west coast of North America. And in a storm in May of 1990, 80,000 Nike shoes were washed overboard. The unique thing about the Nike shoes, although it cost a little bit more than like a $2 bath toy, is that they all had individual serial numbers attached to them. As these shoes started to wash up on shore, oceanographers were able to say, okay, what is the serial number? They knew what serial numbers had been lost and were able to say, okay, this shoe came from this accident, this location. We see it here. And once again, it sort of showed how ocean currents carry material, carry water itself, or move water itself throughout the oceans. Another interesting thing about this Nike shoe thing was that after they fell overboard, the presence in the ocean was used to help validate a model known as the Ocean Surface Current Simulator. The simulator predicted that shoes would make landfall on the northern tip of Vancouver Island and the central coast of BC at roughly about 240 days after the accident, and they first started appearing on Vancouver Island after 220 days. So it was a good unexpected way to test this simulator to see if it would actually work for what scientists wanted it to work for. Another little interesting side note to the Nike shoe story and the movement in this big circular circulation pattern within the North Pacific was that people actually, and this is sort of in the early days of the internet, but people would post or hold post online or hold swap meets and say, hey, I found a shoe, size 11, it's for the left foot, this is what it looks like. And they were actually able to meet and pair shoes up. So people would actually have this pair of shoes that was found that was a relic or was a result of this accident 10, 20, 30 months ago out in the North Pacific. One final thing that should be said before we start looking at surface currents in more detail is what is a Sverdrup. And a Sverdrup is named after a Norwegian oceanographer, Harald Sverdrup, and it's used to measure, it's the measurement that we give, so the unit we give for massive volumes of water. How much water is being transported? We see that one Sverdrup equals about 1 million cubic meters of water per second. And as I said, it's named after the Norwegian oceanographer. So once again, you want to talk about how much water is being carried by an ocean current. You can talk about it in terms of how many Sverdrups there are. 10 Sverdrups of water, 20 Sverdrups of water are being carried. We're going to take a look at surface currents in the ocean. And the first thing we're going to look at is what a surface current is. We have an example here. It's the Gulf Stream operating off of the eastern coast of the United States. Surface currents typically involve about the upper 10% of the water in the ocean. We see that it moves the water above the pycnocline. And this typically is, if we had to put a number or value on it, I would say sort of the upper 400 meters of the ocean. But this is going to change depending on where you are and the position of the pycnocline. This is where we see water moving horizontally within the ocean. So it's flowing from one point to the other in a horizontal movement. The primary force behind the movement of water in a surface current is wind. And what we see is that there's an energy transfer from the air to water versus friction. Now we will eventually be talking about waves, and I just want to point out at this point now that the movement of water in a current is entirely different from how water moves in a wave. So we see a transfer of energy from air to water via friction. What basically happens is the wind tugs on the ocean surface. This starts a flow of water, and this water flowing beneath the wind will form a surface current. If we have wind, for example, blowing across the ocean for a period of 10 hours at roughly the same speed, it causes surface waters to flow at about 2% of the wind speed. The greater the wind speed, the stronger, the more sustained, the quicker that movement of water is. What happens is this occurs in just the very top layer of water. But below the surface, we have other water molecules, And that movement or the interaction between the water molecules on the surface that are being affected by the wind, the water molecules immediately underneath it will start that layer moving. And it'll continue on and on and on until you reach a depth, sometimes a few hundred meters below surface, where that movement becomes negligible and then that surface current ceases to operate. As we know from our module on atmospheric circulation, we do have the Coriolis effect. And the Coriolis effect plays a role in the movement of all fluids on the Earth. So air is a fluid, water obviously is a fluid. So what we see is in the northern hemisphere, due to the way that wind flows, atmospheric wind patterns, as well as the Coriolis effect, we see that currents flow to the right of the wind direction. But there's a big problem here. There's continents. We don't have just this one big massive ocean that the water can continue to flow and flow and flow to the right. Eventually, continents, the ocean basin itself, the way it's configured, gets in this way, and this causes the currents to change direction. The resulting of this, or the resulting end result of this, is the formation of a circular pattern known as a gyre. So these gyres form as a result of the complex interplay between wind, gravity will eventually play a role, Coriolis effect, the way our coastlines are shaped, the way our oceans are shaped, and where our continents are positioned. If we take a look at these circular movements of water, these gyres that form as a result of the flow of water to the right in the northern hemisphere, the position of the continents, we see that it's actually a collection of 4 main currents. And these main currents, especially what we know as the eastern boundary current and the western boundary currents, have some very distinctive and different properties. We find that these gyres, there's 5 of them in total, 2 in the northern hemisphere, 3 in the southern hemisphere, are typically centered around 30 degrees north or south, and this is why they're called subtropical gyres. We see that both warm water currents and cold water currents move in them, and that the boundaries between the currents are interconnected. It's really hard to say, okay, this is where one ends and where another one starts. In the northern hemisphere, once again, they rotate to the right. In the southern hemisphere, they move counterclockwise. So within each individual gyre, we see 4 different types of currents. And we're going to focus on the North Atlantic gyre here because it's the one basically right outside our back door. Here we see 4 currents. And the 4 currents are the western boundary current, the eastern boundary current, and then 2 transverse currents. There are definitely very distinctive differences between the western and eastern boundary currents. We are going to talk about these in a couple of minutes, but first of all, we're going to take a look at gyres and talk about why these gyres show a circular pattern. Why do we see these currents sort of operating on the periphery of this ocean basin or the periphery of the gyre? So here we are in the North Atlantic gyre, and the question is, why do these currents flow around the periphery of the basin? And what we're going to do is we're going to look at a couple scenarios. We're going to look at point A here. And what we see here at point A is we have westerlies blowing. So the wind is coming from a westerly position. It's blowing across the water, and it starts to move that water in the same direction as the wind. Why then does the water start to turn? Why does it start to turn towards Europe from point A? Well, remember, we have a Coriolis effect. And the Coriolis effect, what it does is it causes fluids to turn to the right or be deflected to the right in the northern hemisphere. So what happens when we consider the Coriolis effect, what we see now is that even though the wind initially starts that water moving towards the same direction as it, sort of you can think of it almost at a 45-degree angle from north, what happens is the Coriolis effect causes that water to be deflected towards the right, and what happens now is it flows directly east. And that water is going to continue to flow east, but eventually it's going to hit the coastline of Europe and Western Africa. When it hits that, it needs to go somewhere. That water can't keep flowing. And what happens then is it makes a turn and starts flowing down south along the coastline of Europe, along the coastline of Spain, Portugal, and along the coastline of northwestern Africa. What's happening at point B? Well, the same thing that we see happening at point A. But now what we see is the wind is blowing. These are the trade winds. They're blowing at roughly from about 15 degrees north. We see the Coriolis effect now deflecting the water, and the water starts to flow towards the west until eventually it hits the northern tip of South America, Central America, and starts to make a turn back up towards the North Pole.